Today, I will be discussing the use of defects in silicon carbide as a qubit. I will begin with some brief background on why researchers began to look into this qubit architecture, and some general information about silicon carbide. I will then go on to discuss some important experimental and theoretical results, following all the way through to 2017. Throughout the presentation, I will mention potential future applications that are made possible from the results I discuss, and challenges that must be met in order to make progress with this architecture. I will also be comparing these results to those of the leading competing qubit architecture, nitrogen vacancy centers in diamond, also known as NV centers. To begin, we shall ask what motivated researchers to look at defects in silicon carbide as a qubit. The ability to coherently control and measure the state of a quantum system with high fidelity is a necessary step on the path to constructing a quantum computer. Single electron spins in solids have been studied as a viable candidate system in order to achieve this goal due to their long relaxation and coherence times, as well as their ability to be manipulated using microwave and radio frequency pulses. Nitrogen vacancy centers in diamond were the first system in which researchers were able to measure the quantum state of a single electron spin over a decade ago. Ever since, this defect has received much attention, and many techniques have been developed to improve control, readout, and coherence times of this system. Recent research efforts have been attempting to incorporate NV centers into microelectronic, micromechanical, and photonic structures. However, current microfabrication and growth techniques limit our ability to grow high-quality electronic-grade diamonds larger than the millimeter scale. This has prompted a search to discover optically active defects in other semiconductors that are similar to or improve upon the properties of the NV center. This search has led to much research on defects in silicon carbide, a wide bandgap group 4 semiconductor. This material has about 250 known polytypes, each of which is a binary tetrahedral crystal with different stacking sequences of the same 2D layers of silicon and carbon. Each polytype has its own physical properties and applications. The three most common polytypes are 4H, 6H, and 3C silicon carbide. 4H and 6H silicon carbide are used for optoelectronics applications as well as substrates for the growth of graphene and gallium nitride. 3C silicon carbide is used for micromechanics applications and can be grown epitaxially on silicon. Die vacancies, or point defects consisting of adjacent silicon and carbon vacancies, have been the focus of much of the research due to their similarity to NV centers in diamond, though single silicon vacancies and others have also been examined. Each polytype has a different number of inequivalent die vacancies based on its crystal structure: 1 in 3C, 4 in 4H, and 6 in 6H. More complex polytypes display more inequivalent die vacancies. For example, there are N inequivalent die vacancies in NH silicon carbide. These die vacancies tend to exhibit similar triplet ground states to those of the NV center, as well as the ability to be polarized and read out using optically detected magnetic resonance, ODMR. Due to this, they have received a heavy research emphasis and will be the main focus of this video. One major advantage of silicon carbide over diamond is that it has well-established growth techniques. Whereas we cannot grow high-quality diamonds larger than the millimeter scale, with silicon carbide we can achieve inch-scale, high-quality single crystals, and have had much success engineering optoelectronic and electromechanical devices using silicon carbide. This will hopefully allow for more seamless integration between defect qubits and existing device technology. 4H silicon carbide was one of the first polytypes to be researched in 2011. The 4 inequivalent die vacancies in this structure are labeled HH, KK, HK, and KH. The HH and KK die vacancies are oriented along the C-axis of the crystal, whereas the HK and KH die vacancies are oriented in the basal plane. The C-axis neutral die vacancies share the same symmetry as NV centers in diamond and have similar electronic structure. In this paper from 2011, it was shown that several of these defects can be controlled at room temperature using the same techniques developed for NV centers. The PL 1 through 4 peaks shown in the figure correspond to the 4 inequivalent HH, KK, HK, and KH dye vacancies. The sources of the PL 5 and 6 peaks are unknown. In 2013, it was shown that 4H, 6H, and 3C silicon carbide all contain coherent, optically addressable defect spins that display room temperature coherence. Each inequivalent defect site has its own optical and radio frequency transition energy, which leads to the possibility of having nearby coupled networks of individually addressable spins in complex polytypes of silicon carbide, despite the wavelengths of light greatly exceeding the distance needed for magnetic coupling of dipole spins, which is approximately 30 nanometers for NV centers in diamond. The measurements discussed so far were all performed on ensembles of spins. However, it was not until 2014 that coherent control and measurement of a single spin qubit was demonstrated in silicon carbide. Ausschlam's group was able to demonstrate coherent control of individual spins associated with neutral dye vacancy defects, specifically the HH, KK, and KH forms, since the HK dye vacancy was not found in their sample of high-purity monocrystalline 4H silicon carbide. In the same year, another research group was able to demonstrate similar results using a single silicon vacancy defect spin. The ability to control a single electron spin expands the possible applications to quantum communication, nanoscale nuclear magnetic resonance, quantum memory based on long coherence times, and nanoscale sensing of electric, magnetic, thermal, and strain fields. Whereas nitrogen vacancy centers are addressable using visible wavelengths, dye vacancies in silicon carbide are addressable using near-infrared wavelengths, which makes them more applicable to photonics and communication. Since silicon carbide is piezoelectric, and neutral dye vacancies have been shown to be highly sensitive to electric fields, it has also been shown that the optical and spin properties of neutral dye vacancies can be modulated by applying electrical and mechanical stimuli, which indicates that silicon carbide could be a great material to use for studies on coupling spins to mechanical resonators. More recently, in 2016, it was shown both experimentally and theoretically that the ensemble Hahn-Echo coherence time of the neutral KK dye vacancy in naturally isotopic 4H silicon carbide can be up to 1.3 milliseconds in moderate magnetic fields. This study, by Ausschlam's group, determined that there are two major factors that lead electron spins in silicon carbide to display one of the longest Hahn-Echo coherence times in a naturally isotopic crystal. The first is that moderate magnetic fields, greater than or equal to 30 millitesla, decouple the nuclear spin baths of paramagnetic silicon and carbon. Also, due to the binary crystal structure, there are longer distances between homonuclear spin pairs, preventing them from forming strongly coupled nearest neighbor spin pairs, resulting in fewer nuclear spin flip-flops. This increases the coherence time as the magnetic field inside the crystal fluctuates less. Interactions between the electron spin and the nuclear spin bath caused by paramagnetic nuclei in the crystal still limit the coherence time of the qubit. The Hahn-Echo coherence time for NV centers in naturally isotopic diamond has been shown to be 0.63 milliseconds, and for donor spins in natural silicon, it has been shown to be between 0.5 and 0.8 milliseconds. The paramagnetic nuclei in these crystal lattices are those of the naturally occurring spin 1/2 isotopes carbon-13, present in 1.1%, and silicon-29, present in 4.7%. The figure shown above compares the experimental and theoretical results for T2 of the dye vacancy defect in silicon carbide alongside the theoretical results for NV centers in diamond. As can be seen, the T2 time for the dye vacancy in naturally isotopic 4H silicon carbide is quite a bit longer than that of the NV center in naturally isotopic diamond. However, previous works have shown that T2 for dye vacancies in silicon carbide drops significantly with an increase in temperature, whereas the NV center is known to be relatively insensitive to temperature changes, due to its high Debye temperature and the small spin-orbit coupling in diamond. The cause of the temperature dependence of the dye vacancy in silicon carbide is not yet known. The results from this paper imply that spin qubits in ternary and quaternary crystals may have even longer coherence times, or that alloying silicon carbide with larger elements, like germanium, may extend the coherence time of the dye vacancy defect spins. Other methods for increasing coherence time include isotopic purification and dynamical decoupling. Earlier this year, in 2017, a high-fidelity spin-to-photon interface in isolated dye vacancies in epitaxial films of 3C and 4H silicon carbide was demonstrated, a key development on the path towards utilizing these defects in quantum communication technologies, including nanophotonics applications and long-distance entanglement. 3C silicon carbide has received less focus in the way of coherent spin control, but could be an important polytype for these types of applications due to our ability to grow epitaxial films of it. In this paper, the authors show that the 3C silicon carbide dye vacancy has a Hahn echo coherence time on the order of a millisecond. They are also able to show that both 3C and 4H silicon carbide have spin-dependent optical fine structures, allowing for high-fidelity initialization and single-shot readout, both necessary for long-distance entanglement protocols. Looking forward, a method of engineering many individually addressable dye vacancy defects in silicon carbide must be found, rather than simply finding and identifying defects already located in a sample. This will be necessary in order to consistently create nearby qubits in order to enable multi-qubit operations, a necessary step on the way to building a quantum computer. Here I have cited the references and sources of images used in this presentation. I hope you have found this video informative. Thanks for watching.